Alright, welcome to part 2. So today we're going to talk about L'Hopital's rule. Now, I've said before, we know how to solve limits like this. If I want to let the limit as x goes to 1, if I plug the 1 in, I get 0 over 0. We don't know what that is. You may recall we call that indeterminate form. We don't know exactly what it's going to be. So the old way of solving it algebraically was just to take the factor the top and bottom. Factor the top, look at the bottom, and I can see those cancel. And I'm left with the limit as x goes to 1 of x plus 1, which gives me 2. Well, today we're going to look at what's called L'Hopital's rule. And here's what the rule says to do. It says if the limit as x approaches any number of f of x over g of x is either 0 over 0 or infinity over infinity, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. In other words, we just take the derivative of the top and the derivative of the bottom. Now be careful, this is not chain rule. So what L'Hopital's rule is very simple. So if it's indeterminate form, so it must be indeterminate. That's the big thing, must be indeterminate. So let's look at our example here again, using L'Hopital's rule. If I take the limit as x approaches 1 of x squared minus 1 over x minus 1, I get 0 over 0. Well, if I apply L'Hopital's rule, well, what L'Hopital said to do, or Bernoulli said to do, was take the derivative of the top, I get 2x, take the derivative of the bottom, which is 1, and if I plug in my 1 now, I get 2 times 1, which is 2, which is what we had before. Now, the nice thing about L'Hopital's rule, this will work for any indeterminate, even if I look at those horizontal asymptotes. Like if I have like 3x cubed plus 5x minus 1 over, let's say 2x cubed plus x minus 7. Well, what L'Hopital's rule says to do, if I plug infinity, I get infinity over infinity. So what he said to do was take the derivative of the top and bottom. Here I get 9x squared plus 4 over 6x squared plus 1. I still get infinity over infinity, if you notice. Well, what we do, since both of these are indeterminate, I just take the derivative again, top and bottom. I get 18x. Whoops, let me get my light back on here. I get 18x over 12x. And the x's cancel. I get 18 over 12, which reduces to 3 halves. Now, we knew that before because of Bobo-Botten. Degrees on top, they're the same, so we just look at the lead coefficients. But as you can tell, it works. What's really nice, it'll even work for harder ones, like remember these from earlier this year? If we have something like, let's say, the sine of 7x over x, and what we would have to do algebraically, multiply top and bottom by 7 to make those the same. Well, L'Hopital said if I plug it in, I get 0 over 0. It's indeterminate. So what L'Hopital said to do, take the derivative of the top. I get 7 cosine 7x over 1. Plug in the 0, I get 7 times 1, which is 7. So there's my limit. Remember, this is saying that there is a hole at 0, 7. That's what the indeterminates tell us, that there are holes, dear Liza, a hole. So let's take a look at more complicated ones, okay? Remember, this all started with the question, how do we solve a limit like this? Now, what if I have like e to the 3x minus 1 over just x? Now, I can't solve this algebraically. I can't factor the numerator. Nothing will cancel. I can't use conjugate method. Nothing like that's going to work for us. So how do we solve a problem like this? L'Hopital's. Well, if I first check if it'll work, plug in the 0, 1 minus 1 over 0, 0, 0, so L'Hopital's will apply here. And what it says to do, take the derivative of the top, 3 e to the 3x minus 0, be careful, over 1. And if I plug it in, 3e to the 0, so I get 3. So therefore, it's saying as x approaches 0, f of x approaches 3. In other words, again, there's a hole at 0, 3. Let's try number 2 here. Let's try another one just like this. The limit as x goes to negative infinity of, let's say, x squared over e to the negative x. Well, if I plug in the negative infinity, I get negative infinity squared over e to the positive infinity. So I get infinity over infinity. L'Hopital says to apply this. Now our rule says to apply L'Hopital's. So we take the derivative of the top. Don't forget to keep copying down those limits. 2x, derivative of the bottom, negative e to the negative 2x. I plug it in. This time I get negative infinity over negative infinity. So they're both infinities. So L'Hopital says to take the derivative again. We get the limit as x goes to negative infinity of 2 over, be careful, this just becomes e. Whoop, that should be a 2x. That should just x. So e to the negative x. Now, I know I'm going to be done with L'Hopital's here because on top I'm not going to get a 0. Remember, L'Hopital's only works at 0 over 0 or infinity over infinity. So I'm stuck with the 2 on top. Plug in the negative infinity on bottom. I get e to the infinity, which is 2 over infinity, which we did earlier this year. Remember, the limit as x goes to plus or minus infinity of 1 over x is 0. So I know that that is 0. That's a rule from earlier this year. So my limit there is 0. So what this is telling me, since it's a limit to infinity, this is a horizontal asymptote at y equals 0. Our function's approaching 0 as we go to negative infinity. Number 3, let's take a look at number 3 here. Slightly harder one. The limit as x goes to infinity of e to the negative x times the square root of x. Now this one's troublesome. If I plug this in right now, I'm going to get 1 over infinity times the square root of infinity, which is just 0 times infinity. Now, weird things happen. This number exists. Infinity does not exist. You can't count to infinity. Whoa! So what do we do? Now, don't just jump the gun and say 0. Okay, it's not always going to be 0, so be very careful. Just coincidence that this one will turn out to be 0, but we'll see another example where it won't. Trust me. So, but the rule is you can't take something that exists, multiply it by something that does not exist, and expect something to exist. It's not going to happen. I can't take... Look, I have an imaginary girlfriend. I'm real, she's imaginary. When you put us together, doesn't mean I'm in a real relationship. The same thing is here. You can't take something that exists, multiply it by something that does not exist, and expect something. So we have to get this into the form. We need this form, 0 over 0 or infinity over infinity. So to get that is, what happens, I'm going to place one of these on bottom. So therefore, either e to the negative x or the square root of x goes on bottom. One of them has to go below. Pick the easiest one, the e to the x. So I can rewrite this now as the limit as x goes to infinity of the square root of x over e to the x. By bringing to the bottom, the power becomes positive. And now if I plug it in, the square root of infinity is infinity, e to the infinity is infinity. So now I can apply L'Hopital's rule. So what does L'Hopital say to do? Take the derivative of the top, which is easy, 1 over 2 square root of x divided by the square root of the bottom. Derivative of the bottom. I'm going to rewrite that. That looks kind of weird. This becomes then the limit as x goes to infinity, 1 over 2 root x e to the x. And again, now if I plug it in, I just get 1 over infinity, which we already know is 0. Very easy to do. Let's take a look at a harder one now. I've got 2 more examples for you, okay? Number 4 and 5, though, are pretty challenging, okay? So let's take a look at number 4 here, okay? Now, number 4, the limit as x goes from 1 to the right of 1 over the natural log of x minus 1 over x minus 1. Alright, now, if I try plugging it in, I'm going to get 1 over 0 minus 1 over 0. Now be careful. Your reaction is to say, oh look, 1 over 0 minus 1 over 0. Shouldn't that equal just 0? No, because again, remember, this does not exist. This does not exist. You can't take two things that don't exist and expect to get something that does exist. 0 exists. Look at my pocketbook. Okay, it exists. So I have to get it into this form. I want either 0 over 0 or infinity over infinity. And I do that by using a little bit of algebra. I am going to write this as a single fraction. The natural log of x, x minus 1, cross multiply x minus 1 minus the natural log of x. Whoops, forgot my x there. Natural log of x times x minus 1. And now if I plug in my 1, I get 1 minus 1 minus 0 over 0 times 0. I get 0 over 0. So apply L'Hopital's. L'Hopital says to take the derivative of the top. See, I'm going to apply L'Hopital's now. Take the derivative of the top. I get 1 minus 1 over x. Derivative of the bottom, be careful. Product rule. The first times the derivative of the second plus the second times the derivative of the first. I don't like the way this looks, so I multiply top and bottom by x. And we get the limit as x goes from 1 to the right of the following. X minus 1 over times x, natural log of x, plus x minus 1. If I distribute, plug in the 1, 1 minus 1 over, this is 1, oh no, times 0, plus 0, so I get 0 over 0. You know what that means? Got to take L'Hopital's again. So if I take L'Hopital's rule again, as x approaches 1 from the right, the derivative of the top is 1. I know I'm done. Product rule again. The first times the derivative of the second plus the second times the derivative of the first plus 1. Now these x's will cancel. And now I'm going to plug in the 1. 1 on top, on the bottom. Be careful, I'm left with this 1 plus the natural log of 1 is 0 plus 1. And I get 1/2. So there's my limit. Now, I want you guys to think about it. Remember we talked about this. We got a d and e minus a d and e, right? We got 1 over 0 minus 1 over 0. Weird things happen. Remember, 1 over 0, as we limit the limit here, you might recall this rule. The limit as x approaches 0 from the left to right of 1 over x is either plus or minus infinity. Okay? So we're basically saying from the right, this is infinity minus infinity. We don't know what that is. In this case, though, what does it wind up being? Infinity minus infinity becomes 1/2. We don't mess with infinities. That's why you got to be really careful with the algebra on these, okay? All right, let's take a look at number 5 here. Last one, okay? And it's a doozy. The limit as x goes to infinity of 1 plus 2 over x to the x. Now, for a problem like this, if I plug it in, if I try plugging the infinity in, I'm going to get 1 plus 0 to the infinity. So we're really looking at today, well, what is 1 to the infinity? Again, don't assume you know what it's going to be. Infinity does not exist. It doesn't play by the rules. We're not going to get 1 necessarily. So we have to solve this algebraically. And to do that, we have to use logs in this case. So I'm going to have to set this equal to y. And now I'm going to take the log of both sides, because logs bring down power. Take logs. So I take the natural log of y, that's going to equal the limit as x goes to infinity of, when I use the log, this becomes x times the natural log of 1 plus 2 over x. Remember, natural logs are able to bring down the power. Now, again, if I plug it in, I'm going to get infinity times 0. Now, I know what you're thinking. Hey, last time we did that, we got 0. Just remember, infinity does not play by the rules. This does not exist. This does exist. So we have to get this, remember, we wanted to get this in the form 0 over 0 or infinity over infinity. So one of them has to go to the bottom, the x or the natural log. And the natural log is harder to do, so we'll bring the x to the bottom. So I get the natural, the natural log of y equals the limit as x goes to infinity of the natural log of 1 plus 2 over x to the negative 1. And now when I plug it in, ready? Plug infinity, I get the natural log of 1 over infinity to the negative 1, which is 0 over 0. So we apply L'Hopital's now. So apply L'Hopital's. We take the natural log of y equals, and this becomes the limit as x goes to infinity of 1 over 1 plus 2 over x times the derivative negative 2x to the negative 2. On bottom, what do I get? Just negative x to the negative 2 when I take the derivative. And notice the x to the negative 2's cancel, and we're left with the natural log of y equaling the limit as x goes to infinity of, be very careful, the negatives cancel also, 2 over 1 plus 2 over x, which we already know. 2, plug in the infinity on bottom, 1 plus, that's just 0. Remember, 2 over infinity is just 0, and we're left with 2. Now we're not done because we have to solve it. The natural log of y equals 2, exponentiate, therefore y equals e squared, and there's our limit. So what we're saying here, in this case, 1 to the infinity gives us e squared. It's not always going to be e squared, but we have to show the process there. So hope you guys had fun today with L'Hopital's. I'll see you guys later. Bye-bye.